You are looking at a modern engineering triumph. In this simulated void, the geometry of this turbine blade is mathematically flawless. When components like this leave the manufacturing line, they are heavily optimized. The production process is automated, and the controls are tuned down to the last parameter. On paper, the part is perfect. Then, months into active service, the physical reality sets in. The component begins to pit, microscopic cracks propagate along the geometry, and the structure loses its integrity. The design software calculated the tolerances correctly, the engineers selected the right generative model, and the manufacturing parameters were exact. The weak link was the physical material chosen for the harsh environment that component actually had to survive. Standard workhorse steels remain effective materials. They are the backbone of countless parts operating in conventional, low-stress environments. But standard metals hit their limits immediately when deployed into high-performance industrial systems, like the hot section of an aircraft engine or an energy system cycling through extreme temperatures. You cannot optimize your way out of a physical material limit using generative design or topology optimization. If the alloy cannot survive the ambient heat, the shape of the component is irrelevant. Advanced manufacturing requires a shift in focus. Engineering these complex systems is becoming materials-led rather than software-led. Selecting the exact material for the operating environment now serves as the primary enabler of the system's existence. Modern industrial applications do not test materials with one isolated challenge at a time. They apply multiple overlapping forces. This chart maps environmental stressors. In a turbine, high heat and oxidation combine, attacking standard metals. In oil and gas, pressure mixes with corrosive fluids and salt exposure. The damage mechanisms are specific. Under extreme heat, metals undercreep, slowly deforming over time. Corrosive media causes pitting, triggering localized attacks that hollow out cavities. Repeated heating and cooling cycles add fatigue. Those cavities become the genesis for tiny cracks that propagate cycle by cycle until the system fails. Standard metals fail when these vectors combine. Surviving compound stress requires materials engineered to hold a specific balance of properties under constant attack. Metallurgical limits have historically defined industrial boundaries in environments where extreme heat and friction dictate the physical scale of production. Specialty materials, like the high-performance alloys produced by VDM Metals, address this by acting as engineered balances of strength, corrosion resistance, and thermal stability. Nickel alloys are formulated for environments where equipment must survive heat and oxidation simultaneously, making them critical for hot gas paths and aerospace. Cobalt alloys are deployed to withstand severe mechanical wear and friction, maintaining structural strength in high-temperature applications where physical stress is unavoidable. Zirconium is a targeted solution used in chemical processing infrastructure when the process media is so aggressive that standard corrosion-resistant alloys would rapidly dissolve. Special stainless steels fill the middle ground. Their chemistries handle tougher thermal and mechanical demands than everyday grades, remaining practical for large-scale industrial builds. These specialized alloy classes push material selection out of the late-stage procurement workflow and turn it into the foundational decision that allows a system to operate at all. If high-performance alloys provide the material, additive manufacturing provides the method for producing complex modern geometries. In metal 3D printing, metal powder is not merely raw material. It is an active process input that dictates the physics of the build. As a laser traverses the powder bed, it melts the material rapidly, fusing layers together. The powder's physical morphology governs how that melt pool behaves. Particle size distribution determines the outcome. Uniform, spherical particles flow and melt consistently. Irregular, jagged particles cause erratic melting. When flow is inconsistent, the laser leaves behind microporosity. The fused layer cures with dark, empty voids and inconsistent material density. Those microscopic voids become the surface defects and crack initiators that compromise parts in the field. The physical behavior of the powder during the print dictates the component's repeatability, part qualification, and long-term reliability. Additive manufacturing is scaling from prototyping into high-volume production for demanding, heavily regulated sectors. VDM Metals produces metal powders alongside its broader specialty alloy portfolio, aligning with industries adopting additive manufacturing for complex, high-value components. Their Extra Mile project at UNA highlights this. The facility integrates a state-of-the-art VIGA-70 vacuum inert gas atomization system alongside their relocated VIGA-35. By its scheduled commissioning in 2027, this expanded setup raises their total high-alloy powder capacity to roughly 200 tons per year. This capacity expansion, paired with recent executive board reorganization, shapes how consistently materials and powders can be developed and supplied at an industrial scale. Moving advanced geometry from prototyping to reliable, high-volume production requires an industrial supply chain capable of delivering highly consistent VIGA-atomized metal powders. Material selection historically operated as a procurement workflow: compare known grades and optimize for purchase price. Today, component optimization requires treating material selection as a strategic design lever. Selecting the correct high-performance alloy directly extends the service life of a component by slowing crack growth, resisting corrosion, and maintaining properties at temperature. Superior thermal stability and fatigue resistance reduce unexpected shutdowns in harsh remote operating cycles where maintenance is dangerous and replacement is costly. Design freedom, consolidating parts and thinning walls, is only viable when the material is physically capable of supporting those advanced geometries under stress. While specialty materials require a higher upfront specification, they act as a foundational lever, extending uptime and enabling the maintenance intervals that make high-performance systems economically viable. Design constraints, process planning, and supply strategy have merged into a single, tightly coupled engineering workflow. Engineering a modern system requires answering Phase 0 questions immediately. What specific heat, corrosion, pressure, and fatigue vectors will the part face? And if additive manufacturing is chosen, engineers must define exactly what powder characteristics are mandatory for qualification long before a laser fires. Heat, corrosion, and mechanical stress do not care how elegant a CAD model looks on a computer screen. Industrial innovation relies on smarter software, automation, and optimized geometry, but those advances still have to live in the physical world. The next leap in industrial innovation will be built by materials physically capable of surviving the environments we are pushing them into.